Okay, here's where we started last time, or ended last time. We were graphing, we're not going to do any more of this today. We were graphing logarithmic functions, and the strategy is the same as it's been for the whole semester. You start with a plan, you start with a base function, you work it into the function that you're interested in. You track, each step is one transformation, only one transformation. And you track it on one graph, put your final answer on the other graph. Now here, I've got some homework. A couple of things I just want to remind people of today. At 10:45, everybody's got, or 10:30, excuse me, 10:30. Everybody's got somewhere to be. This is the only class you'll have today. Rest of the day, unless you've heard something otherwise from somebody. But faculty received instructions. All other classes today are going to be canceled, which is a break for you because what you're doing at 10:30 is not going to take all the rest of the day, right? So that just be sure you're check your email. Emails have gone out to everybody. But this is the only class that that you're probably going to have today. Secondly, I want to emphasize, start preparing for the final exam now. Especially, good morning. Especially if you would like to bring your grade up, start working on your formula card. If you'd like a blank index card, I got them right here. You're welcome to them. And put your weaknesses on the card, things that you think you might be useful to you on the card. Go back to chapters 1 and 2. Look at what you did poorly on your exam. Come in my office, look at your exam. Look it over, your chapter 1 and 2 exam. Go back, get those skills. If for no other reason, it'll help you on the chapter 4 test, right? But it'll certainly help you on the final. Start compiling your card, get a jump on it. You won't be able to move the needle that much doing it all in the last week. So if you wait till, the very last week of the semester, 4 weeks from now, you're going to be in cram mode. And not only that, your habits will still be there. Your habits will still be the same. So you want to change some habits now. A month left in the semester. There's still time to move that needle on your grades. I'm here to help. There's other resources that we've been through on campus and online. So moving on. Oh, this is a homework. I should have clicked to last time, but didn't. We'll make that do next time. We're going to use logarithms now to solve equations. Now, basically, if I had to put this down to a rule, two things to remember. Logarithms are inverses of exponential functions. That's rule number 1. Rule number 2 is the way to get what you're looking for, the way to get an unknown out of an exponent is going to be a logarithm. The way to get something out of the logarithm is to what's called exponentiate. We'll get to that. We'll get to that. Okay. So here, this is one of those examples that using addition, subtraction, multiplication, and division, which are called the algebraic operations, it is impossible to solve something like this for x. Right? We need a logarithmic function, which is actually what I told you before, transcendental function. You'll hear that. You'll see that word sometimes. What do? What would you like to do? Now, don't write this down, but what have we done up till now? We've solved equations like this, or almost like this, up to now. For example, if you have over here 2 to the 3x equals 8. If that was the equation, we've solved stuff like that already. Right? What was the trick? Get the same base on each side. And so you would have seen that 2 is, of course, a base. The right side is 2 to the 3. Equal bases means equal exponents. So we used that property to go from here to here. And so 3x equals 3, or x equal 1. So that's how we've solved things in this form up till now. That only works. That only works when you can get this 8 as a power of 2. We can express both sides in terms of the same base. 2 in this case. Over here, 7 is not a power, well, put this way, is not a convenient power of 2. It is a power of 2. Now, in order to solve this, what did we have to do? We had to figure out, we had base 2 on one side. We had to figure out what power of 2 is 8. And it was 3. What power of 2 is 8? 3. Over here, we're going to have to say, what power of 2 is 7? We need what power of 2 equals 7? Question. Answer. Two to some mystery power equals 7. You remember what we practiced last time? You remember the homework that's due today? This is log base 2 of 7. So you remember the most important slide of this section, maybe the most important slide of this whole chapter, maybe, is thing is not working real well. All right, go back. I shouldn't have gone back so far. Right here. Remember this? This is the rule you need to know how to apply. That is basically the definition of a logarithm. But you need to know how to apply it. The question mark here is log. The base here is 2. The base here will be 2 of 7. So this is the power to which 2 must be raised to equal 7. That's log base 2 of 7. And we're going to use that property here. How are we going to use that? Right. Well, 2 to the 3x, we are going to take log base 2 of each side. And you know what? There's one little property we're going to have to use here. Right? We've done it. Right here. We're getting a little out of order. Down here. This rule right here. The log of a number to a power, you can bring that power down front. Right? That's one way to do this. Let me get back here. I'll show you something. This particular problem, we know that log base 2 of 7 is the power to which 2 must be raised to equal 7. In other words, 2 to the log base 2 of 7 equals 7. This is vitally important that you understand why that's true. Because 2 to the x, 2 to a power, is an exponential function, 2 to the x. Are you with me on that? That's the stacks of paper, 2 to the x. 2 to the x is an exponential function, and exponential functions and logarithmic functions to the same basis are inverses. I'm going to say that again. 2 to the x is an exponential function. right? We've had that a week and a half ago. Log base 2, y equals log base 2 of x is its inverse. What properties do inverses have? They undo each other. They undo each other. So, two, when we raise it to the log base 2 of 7, whatever log base 2 of 7 is, 2 to that power has to equal 7. I want you to think about this. Log base 2 of 7 is what? It's the power to which we must raise 2 to equal 7. Log base 2 of 7 is the power to which we must raise 2 to equal 7. If I raise 2 to that power, it's 7. So up here, we're going to rewrite this using this relationship here. 2 to the 3x equals, instead of writing 7, I'm going to replace 7 by this. And so that is 2 to the log base 2 of 7. That is a very important step. All we're doing is rewriting 7. However, now look what we have. You remember how we solved them over here? We got equal bases. That meant equal exponents. Equal bases, equal exponents. Here, we have equal bases. So here, equal bases. Equal exponents. So 3x on the left equals log base 2 of 7. That's huge because it took our x out of that exponent. These don't take this long. I'm explaining things in detail for 2 reasons. 1, logs are a little bit foggy. 2, if you didn't do the homework that was due today, you're probably lost, or somewhat. So I was doing it for. I'm going over this in detail for review, but we're done. X now equals 1/3 log base 2 of 7. Okay. Right now, you don't have to worry about what that number is. You don't have to worry about what that number is. But that is just a number. Now, there's a way to find that number, and I do it down here in these graphs. I do it down here in these graphs. This turns out to equal that number. That number turns out to be 0.935. All right? 936, okay? We're going to figure out how to do that in a minute. We're going to learn how to do that. I'm going to run this through again, and we're going to do some more. Our problem here is that we've been solving these by making equal bases on each side. But we can only do that when the other side could be written in terms of an integer to a power. So we can get the right side being 2 to a power, the left side's 2 to a power. That's a happy meal. Here, 7 is 2 to what power? That's the question we're after. 7 is 2 to what power? Well, now we know which power. It is log base 2 of 7 is the power to which 2 must be raised to equal 7. And if you haven't studied this, if you didn't work on it in the last few days, you're not going to, a lot of this is going to go over you. All right. A lot of this is going to go over you. I suggest you remedy that very quickly. It's only going to keep going. But when we know that 7 can be written as 2 to the log base 2 of 7, because 2 to the x and log base 2 of x undo each other. They're inverse functions. Then we can write 2 to a power. The 7 can be written as 2 to some power. And that gets us into some open road. Because once I write that as 2 to some power, I have equal bases on each side. Same bases, 2. And that means I can equate the exponents. And then x is 1/3 log base 2 of 7. Here's another one. Here's another one. All right. I'm going to do this one a slightly different way. Might make more sense to you. Logs and exponential functions are inverses of each other. So one way to do this would be here. I want to know e to this power equals 20. What is that going to be? There's no guessing with these. There's just no guessing. One thing to do is use the fact that log and the exponential function are inverses. So ask yourself, what is the inverse of e to some power? The inverse of e to the x is natural log of x. So we could have done the last problem this way. Natural log of the left side is going to equal natural log of the right side. We're going to take the natural log of each side. So the natural log of e to the 3x minus 2 is going to equal natural log of 20. Now, natural log of 20 is just a number. It's just a number. It's the power you have to raise 2 to get 20. Right? Right? Probably going to be a little under 3. Okay? Now watch. That's it, yeah. This right here, log, natural log, and e to the x are inverses. So these undo each other. So the left side is just 3x minus 2. Whoa, what happened there? When you take log of e to something, it's a something. So natural log of e to some power, those undo each other. That just equals the power. Because e and log, natural log, e to the x and natural log x, are inverses. So log of e to anything is just the anything. On the right side, I still have log 20. Well, now we're free. Once you get that x out of that exponent, you have 3x is 2 plus log 20. And then x is going to be 2 plus log 20 over 3. Yeah. The key here is the step. And going from there to there. Knowing to take the log of both sides. Why are you taking the log of both sides? Because I have x up in the exponent. I don't want the x in the exponent. I need to have x on the, that's what I'm solving for. I need to get the x out of the exponent. And so I take log the same base. That brings the x out of the exponent, and I solve for x. Now I'm going to come back to this slide, but I'm going to go back to this slide for a second. Go back to this slide for a second. Another thing we could have done here, if you recognize that, is we could have taken let's go here. 2 to the 3x equals 7. Another way to do this is to take log base 2 of each side. Because log base 2 and 2 to the x are inverses. So I could take log base 2 of the left equals log base 2 of the right. This might be simpler for you. Why did I choose log base 2? Because my base is 2. My base is 2. Well, log base 2 and 2 to the x are inverses. So these undo each other. It's almost as if they cancel. So this left side is 3x, and that is a key step. That is a key step. Because log base 2 and 2 to the x are inverses. They undo each other and give you the 3x. And this equals log base 2 of 7. And you wind up with the same answer. X is 1/3 log base 2 of 7. This is a encore solution. Okay. That might make more sense to you because that is how we did this one here. We recognize the base is e. We take log base e of both sides. Log base e, e to the x, invert each other. You get 3x minus 2. The exponent comes down, and the e to the x and log go away. And you solve for x. Well, then, Mr. Miller, why did you do this way at the beginning? I did it this way at the beginning, and by the way, you're welcome to do it this way. I did it this way at the beginning. Why? Because up till now, how had we solved these? This way. So I did it this way to connect it back to your prior learning, to what you already know or should know by doing homework and so forth, right? So before we got the same, we worked each side into the same base. Equal bases is equal exponents. Knowing the definition of a log allowed us to work this into same bases. That's why I did it this way here. You're free to do it either way. You're free to do it either way. But when we got the same bases, that means the exponents have to be the same. You solve for x. Right? I try to be at least forewarn people that this, I understand, is a little bit foggy for people because logarithms aren't taught really well anymore in some places. And this is stuff you can't just memorize. You can't just look at it and, it's stuff people forget. We don't use logarithms anymore in general society like we used to. However, if you're in this class is primarily for STEM majors. Science, technology, engineering, mathematics. Logarithms are used all over the place in those fields. Logarithms are used in business as well, just not here. So if you're a business major in here, these are used all over business. Right. Put this way. In certain areas of business, they're used very much. All right, there's one for you for Friday. What are you going to do? You're going to do log base 10 here, right? Hint. Ready? Hint. Why am I using log base 10? Because there's the base right there. It's 10. Right? So let's move on. We're going to get the 4-letter word students love. Test. Oh, I'm sorry. Skip. We're going to skip most of Force 5 and Force 6, except for the material we cover in the slides. It's on the slides. You need to do those kinds of problems in the book. Remember, at the end of every section in the course guide, I've given you exercises. If you need more of a certain, I only give like one of every type, two of every type, maybe. Assigned problems, and you don't have to turn those in. If you want to turn those in, you want me to look them over, that's fine. I'll do that. But you have the answers to those in the back in the book, right? And you should do those until you're fluent at them. Until you're doing them, without getting stuck. Because on a test, what happens? Your brain gets kind of blocked because of stress and so forth. You want to be fluent at those. Okay. Here are some properties of logarithms. Properties, pretty basic. But since we have a little trouble wrapping our head around logarithms, these you can look at them and kind of get stumped. So here, log base A of 1. Now you remember A cannot be 1 or anything. A has to be positive, not equal to 1, right? So I want to know what this equals. What do? Well, you can set that equal to some mystery number question mark. This means, right? It means A to the question mark equals 1. What power do I have to raise a positive number to equal 1? That doesn't already equal 1. So 2 to what power equals 1? 2 to what power equals 1? 0. Right? The only power you can raise a number that doesn't equal 1 to get 1 is 0. This means question mark equals 0. And so log, log base A of 1 is 0. Right? Now, if you remember and you took time to prepare in what the graphs of logarithmic functions look like, you remember that log functions, what was their graphs? It looked like this. If A was bigger than 1, and it looked like this if A was between 0 and 1. The vertical axis is a asymptote. So you remember that the only bases you're allowed to have are greater than 1 or between 0 and 1. In either case, what is the log of 1? In either case, the log of 1 is 0. So I'm trying to connect these pieces. So if you've taken the time and effort, like you should, to put pieces together and to look at the stuff we've just done in the last couple days, this will start connecting. Log base A of A. This one I think is a little easier, actually. Call that some question. Uh-oh. You know what that means? Sorry, guys. I sense a crash coming here. So I'm getting out. I'm going over here. Back in. When my board starts delaying and acting funny, I'm about to lose all my work. Okay. Here we are. So log base A of A, well, what does that mean? That means what? It means A to the A equals A. What? It means A to the A power equals A. Huh? Oh, I'm sorry, not A to the A power, A to the question mark power. Sorry about that. Typo. What power do you have to raise a to get a? Well, a is a to the 1. Equal basis means question mark equals 1. So the power you have to raise a to get itself is 1. That makes sense. How about this one? Log a base a of 0. What power do I have to raise a to get 0? So call this our unknown, question mark. This means, have you noticed how often we're going back to that definition of a logarithm? Y equals log base a of x means a to the y equals x. Over and over and over and over. But those are all reps on the machine. You'll understand them that way. So this means what? A to the question mark equals 0. What power do I have to raise a to get 0? You're tempted to say 0, right? But a to the 0 power is what? 1. Right? So the log of 0, well, I'll give you a hint. Look at this graph. When you plug in 0 on a logarithm graph, what value do you get? You get the vertical asymptote. That's what you get. 0 x equals 0 is the y-axis. So when you plug in 0, the logarithm is undefined. There is no power that you can to which you can raise a positive number and get 0. There is no power to which you can raise a positive number and get 0. So this is undefined. It is like, what color is Tuesday? Okay. Those are basic properties. Should you come across them? They are not that involved if you know the definition of a logarithm. Y equals log base a of x means a to the y equals x. Less of that. Oh, that's a good one. We've already, we just did this actually. We just did both of these a couple slides ago. Now, I want you to think for a second. Think. Log base a of something is the power I have to raise a to get something. So what power do I have to raise a to get a to the r? What power do I have to raise a to get a to the r? R. Now, another way of seeing that is doing what we've been doing the last slide or two. Call that question mark. That means a to question mark equals a to the r. Equal basis. So our mystery number is r. And the reason why is that log base a and a to the x undo each other. We did that in the 2 to the x problem a few slides ago. Log base a of x and the exponential function a to the x are inverse functions, and they undo each other. Okay? How about this one? A, now think about this for a second. What is log base a of m? What is log base a of m? That's the power you have to raise a to get m. So log base a of m is the power to which a must be raised to equal m. But if I raise a to that power, that better equal m. So the answer here is M. Now, if you didn't think of that, do what we've been doing. Use the definition. Call that question mark. That's our mystery. So what do? This means that A to the question mark equals log base A of M. Right? Hang on a second. Hang on. No, sorry about that. I don't like what I just wrote. You remember we had this, just let's write over here a second. Y equals log base A of X means A to the Y equals X. Right? So if I have A to the Y equals something, A to the Y equals something, this means the log of the something, right? This means the log of the something, log base A, log base A of the question mark has to equal log base A of M. Right? And this is what I was saying. If log base A of what? Log base A of what equals log base A of M? M. So question mark has to equal M. And that was the first sentence I said, that the answer to this is going to be M. Because log base A of M is the power you have to raise A to equal M. And A raised to the power you have to raise A to equal M had better be M. Because A to the X and log base A of X undo each other. I'll be the first to tell you these scramble your brain. And if you haven't looked at the stuff in the last few days, there's nothing I'm going to really say that's going to help you a lot. Go back and get the last 2 or 3 days classes. Get that material down, and this will make more sense. Go back and see this video in a couple days. Right? And then why does this quote make sense? Because these two are inverses. That's the answer there. So we have some properties of logarithms. We're going to be using these. This is it. Remember, fundamentally, a logarithm is an exponent. A logarithm is a power, right? And so logarithms behave like exponents. The log of a product is not the product of the logs. It's the sum of the logs. This does not equal log base A of M times log base A of N. It does not equal that. So the log of a product does not equal the product of the logs. The log of a product equals the sum of the logs. Similarly, the log of a quotient does not equal the quotient of the logs. All right, does not equal that. It turns out this equals something else. We'll get to that. But the log of a quotient is the difference of the logs. And lastly, this is the power rule. The log of M to a power is the power times log M. You can take an exponent and bring it down front. Okay. You can take an exponent up there and bring it down front. We're going to be using those. Skip. We're not going to do that. Not going to do that one. Don't have time this semester. This one here. This is called, well, here, let's just think of something. Which is larger, log 312 or natural log 312? And you have plenty of information to solve this. Which is going to be bigger, log of 312 or ln of 312? And I know you have the answer here on the right. But this is the power I have to raise 10 to get 312. This is the power I have to raise e2 to get 312. Which is going to have to be raised to a higher power to equal the same thing? 2.7 or 10? You're going to have to raise 2.7 e to a higher power to equal 312 than you will have to raise 10 in order to equal 312, right? So 10 to the star, we're going to do the little symbols here. 10 to the star equals 312, or e, right, to the triangle equals 312. Well, e is going to have to be raised to a higher power to equal 312 than will 10. Because 10 is a bigger number. You have to raise it to a lower power. You don't have to raise it to as high a power to equal the same number. And lo and behold, on your calculator, you see that 2.7 has to be raised to the 5 3/4 to equal 312. But 10 only has to be raised to like 2.5 power to equal 312. All right. This is another one that is a quick little inquiry to whether you understand what log 312 or natural log 312 are. This is log base 10. This is log base e. Change the base. Change the base formula. Now, here's something I mentioned before. On your calculator, you have two bases of logarithms on your calculator. LOG, common log base 10. LN, natural log base e. You have two on your calculator. Notice that they have their inverses as the alternate function, right? The e to the x and 10 to the x. That is just a convenience because it turns out you only need one logarithm button on your calculator. You don't need both of them because you can get one from the other. All right? It's there for convenience. And you can get one from the other using this formula. The log of 1 power, suppose I have log base b on my calculator, but I don't have log base a. If I want log base a of a number m, it's log base b. If I want log base a of m, and I have log base b on my calculator, I take log base b of m and divide it by log base b of a. Huh? Right? So on your calculator, you have two logs. So if I want log of any base a, log base 2, you know, we were talking about log base 2 a few slides ago, right? I don't have log base 2 on my calculator. But I can find log base 2 using my common log key or my natural log key. Now, maybe it'll be clear after this example. Log base 7 of 312. We used our calculator to find log base e of 312 and log base 10 of 312, right? This is answering 7 to what power equals 312. I don't have a log base 7 key on my calculator, but I do have a natural log key on my calculator. So this is going to equal natural log of 312 divided by natural log of 7. And you see, when I do that on my calculator, This is as far as you can go without a calculator, right here. I'll never expect you to know how to get those without a calculator. I don't know how to get them without a calculator. I can get close. But the answer to part A, 2.95. That's using the natural log key. I could also use the common log key. This would also equal LOG of 312 divided by LOG of 7. And that is that answer, which unsurprisingly is the same. It is the same. And to verify it, if you take 7 and raise it to this power, 7 raised to the answer power, which is this power here, it equals 312. Right? All right. Let's do one more. In fact, I'm going to get my calculator out and do this. Log base 6 of 4917. Here it is using LOG. I'm going to get the calculator out and do it with natural log. We got just enough time. All right. Oh, there's some fun right there. All right. So what was my number? 49? 4917 using natural log. It's going to be the natural log of 4917 divided by the natural log of the base. Now, this was log base 6. Okay. So I'm going to divide that by the natural log of the base 6. And that's the same as we got using common log. And to verify our answer, we can take 6 and we raise it to that last power, 4.744, and it equals 4917. All righty? So that is how you convert bases. It's a change of base formula. All right? I will probably, since I'm a nice guy, I'll probably give you this formula on the test. You need to know how to use it. All right? And you're going to have some homework. Next slide. Here's some homework for next time. See ya. Enjoy the rest of your day. Enjoy your afternoon. Get some studying done this afternoon. Those of you who are athletes aren't used to having your afternoons off. A lot of it's booked, right? Because you have practices. Today you're going to have most of your afternoon off. Make good use of it. See ya.